physics, we use various formulae in order to determine and describe various physical quantities and the relationships between them. A very common quantity that you come across is work or energy. And if you remember the formula, it is force multiplied by distance. If we were to approach the same formula in the vector form, it would be the dot product or scalar product of the force F and the displacement d. Or we can say it is the magnitude of force multiplied by the magnitude of displacement multiplied by the cosine of the angle between them. Now, the scalar product or dot product is very useful, and more importantly, it is fairly simple because you are getting a scalar quantity like energy after using two vector quantities. But there are other quantities in physics and relationships which are not so simple. One example is moment or torque and rotation, right? So if you are applying a torque or a moment to an object, we are applying a turning effect to that object. But it is not easy to define a direction for the rotation. An object could be going east and then going west and south and so on. We cannot define a single spatial direction like north or south for rotation. So there are quantities like this which obey a slightly different relationship, and that is a relationship of the cross product. And we will come back to this example of rotation and how we can use the cross product for this purpose later. So let us understand the vector product or the cross product and what it actually means. Let's say that we have two vectors, vector A and vector B. A cross product between these two vectors can be written as, let's say we have the product as C. It is a vector. A cross product or a vector product will give a vector as its output, is equal to A cross B. So we use the cross sign for defining the vector product, which is also why we call it the cross product. We can define this product in such a way that the magnitude of C, that is simply C, is equal to the magnitude of vector A, that is simply A, multiplied by the magnitude of vector B, that is simply B, multiplied by the sine of the angle theta formed between them. So this becomes AB sine theta. Now, here is the other crucial difference. In the scalar product, we were getting a scalar value as the output, right? Here we are getting a vector value. So obviously, vector C will have a direction, but what is that direction? In a cross product, the product will be pointing in a direction which is perpendicular to both A and B. So in this case, C will have a direction which is perpendicular to both the vectors A and B. So the vector C will not be in the same plane as A and B. In the case of a dot product, we knew that the output is also not defined as a vector, but in this case, not only do we have a vector as the output, it is also not in the same plane as A and B. It is pointing in a direction which is perpendicular to both A and B, or we can say that if there is a plane in which vector A and B exist, vector C will be pointing perpendicularly to that plane. What else? In addition to these two things, we also have a way to predict in what direction the vector C is going to point, and this is known as the right hand screw rule. So let's understand what is this. What is the right hand screw rule? So what is the right hand screw rule? Let's say that we have a right-handed screw. So let's make one of those. So what is the right-handed screw rule? Let's say that we have a right-handed screw which we have placed on its head on the ground. So this is the plane of the surface in which we have placed the screw. So here it is. Let's say it is sitting on a table, and the head of the screw is on the surface of the table, and this is the plane in which the screw has been kept. Let's say that we have two vectors A and B. So let's make two vectors here. So this is vector A, and here we have vector B. and these two vectors are also in the same plane as the table. If we are turning the screw in the direction of A to B, so we are turning the screw something like this. So we are turning the screw upside down through an angle theta from A to B. So we are turning in this direction. So if we are turning the screw from A to B in the direction shown, then the vector C will be pointing in the same direction and advancing in the same direction as the point of the screw. So the orientation of vector C seen here will be pointing in the axis of the screw. This is also called the right-handed screw rule, and we can make an easier version of this simply called the right-hand rule, which is very simple. Take your right hand and curl your fingers, all the four fingers of your hand, in the same direction as A to B. So imagine that we have two vectors at the base of our hand, A and B, and we are curling our fingers in the direction of A to B. In this case, the cross product of A and B, that is A cross B equal to vector C will be pointing in the same direction as our thumb. This is an easy way to visualize how the cross product will work for us. So we understand here that the resultant of a cross product is a vector by itself. It will have a magnitude, it will have a direction, and it will not point in the direction of A or be even in the same plane as A or B. It will be in a completely different plane perpendicular to the plane of A and B. Moving on, there are some other interesting properties of the cross product. Let's understand what they are. Aside from what we just discussed, there are other important properties that separate the cross product from the dot product. An important property is that the dot product is commutative while the cross product is not commutative. What does that mean? Let's say that we have two vectors. Again, our old friends, vector A and vector B. If I were to take the dot product of these two vectors, I get a scalar value. Let's say it is C. So C is equal to vector A dot vector B. If I were to reverse the order of multiplication, that is, I had a new product C dash equal to vector B dot vector A, I would find that C is equal to C dash exactly. In other words, I could say that A dot B is equal to B dot A. This is what we call commutative property of the scalar product or dot product. The cross product or vector product does not obey the commutative property. In other words, if I had two vectors, again A and vector B, then the cross product of these vectors, let us say it is a third vector, vector C. That is, vector C is equal to A cross B. In this case, this vector would not be equal to B cross A. In other words, the order of multiplication is important in the cross product. A cross B will not be equal to B cross A. On the other hand, A cross B will be equal to the negative of vector B cross A. So vector multiplication is not commutative, but scalar multiplication is commutative. Another interesting property of the vector product, which is different from the scalar product, is that the vector product behaves very differently under reflection. What does that mean, under reflection? Let's say again, we are dealing with two vectors A and B. Let's say that we have a surface, a plane, and on this plane we have two vectors. So this is vector B, and here we have vector A. And these two vectors have some angle between them. So the angle between them is theta. If we were to define a cross product for these two vectors, that would be vector C. So according to the right hand screw rule, we can predict where the vector C will exist. So it will exist in a plane which is perpendicular to both A and B, something like this. So this is vector C. Interestingly, if I were to reflect both vectors A and B, so what is a reflection? If I were to reverse the directions of A and B. So in other words, I am negating A and B. Let's say that I have a set of two new vectors, that is, we have negative A vector and we also have negative b vector. So negative a vector and negative b vector are the reflected versions of vector a and vector b. I have just taken their reflection, like I have put a mirror and I have taken their reflections. These are the negated or reflected versions of a and b. Even in that case, their cross product will remain exactly the same in magnitude and in direction. Again, you will get the same vector c with the same magnitude pointing in the same direction. Mathematically, I can say that if A cross B gives me vector C, then in that case, negative vector A cross negative vector B will also give me vector C. So the cross product remains unchanged under reflection of both the participating vectors. A final property that I want to discuss is a property which is common to both the scalar product and the vector product, and that is the distributive property. What does distributive property mean? You might remember those equations or the rules of algebra that we learned in junior classes. For example, if I have a scalar quantity, let's say it is A, and I have two quantities B plus C in a bracket, this is the same as A times B plus A times C. So I have distributed A across B and C. This is the distributive property. It turns out that both the scalar product and the vector product are obeying this property. In other words, if I have a vector A and I multiply it in dot product form with the sum of vectors B and C, this is the same as A dot B plus A dot C. Turns out that the vector product also obeys commutativity, which means that if I have an operation vector A cross vector B plus vector C, this is the same as saying A cross B plus A cross C. Both of these are the equivalent operation. So with respect to this particular property, that is the distributive property, vector product and scalar product are similar in behavior. Now, if I were to give you vectors in order to cross multiply, how would we go about it? Understand that if you take two vectors which are pointing in the same direction, let's say that I have a vector A, how do I take the cross product of two vectors? Let's say that we have two vectors defined in three-dimensional space. What operations do I have to perform to get the cross product for these vectors? We will use the basic definitions of the cross product to understand how to tackle this question. Let's say that we are dealing with a three-dimensional space. So we have three axes, the x, y, and the z axis. Each of these axes is mutually perpendicular or orthogonal. So we are going to require three unit vectors. We will use the unit vectors I cap, j cap, and k cap. The vector I cap will be associated with the x axis. The vector j cap will be associated with the y axis, and the vector k cap is associated with the z axis. Understand that the unit vector has only direction information. Its magnitude is simply 1. So in this particular case, any point in this space, if I were to pick any arbitrary point in this space, this point would have three numbers associated with it: the x-axis, y-axis, and z-axis coordinate numbers. So that would be x1, y1, and z1. And each of these would be multiplied by its corresponding unit vector in order to get the position vector for this point. So in this case, if I were to draw a vector from the origin to this point, let's call this point P, then this point P, the vector equation would be x times I cap plus y times j cap plus z times k cap. This would be the vector equation for this position vector. Now, let's say that we have two vectors in the xy plane. We have two vectors defined somewhere in the xy plane. Let's say that we have vector A and we have vector B, and these two vectors have some angle formed between them. Let's say that the resultant of the cross product between A and B is vector C. So, vector C is given as A cross B, and the magnitude of this vector C is given as A times B times sine theta, where A is the magnitude of vector A, B is the magnitude of vector B, and sine theta is the sine ratio of the angle between them. In the case we are given the position vectors of both of the vectors in question, we can use some other properties of the cross product. For example, if two vectors are pointing in the same direction, the cross product of these vectors is 0. Why is this the case? Think about it. We know that the magnitude of the cross product is A times B times sine theta. If two vectors A and B are pointing in the same direction, what is the angle between them? It is 0, and the sine of 0 is 0. That means that if two vectors have the same direction, then their cross product will be 0. Also, if we were to take any of these two unit vectors, let's say that I take I vector and j vector. If I take the cross product of I and j, according to the right hand rule, the resultant cross product will be pointing in the perpendicular direction, so it will point in the direction of the k vector. The same rule will follow for any two of these orthogonal vectors multiplied together. So if I take it I times j, I will be getting k. If I take j times k, I'll get I. If I take k times I will be getting j. Another important point to understand is that if we have two vectors which are orthogonal to each other, the third vector will be perpendicular to both of them or in the perpendicular direction to both those vectors. For example, if I were to take the cross product of the I vector and the j vector, then their resultant will be pointing in a direction perpendicular to both I and j, that is k. So the cross product of vectors I and j is going to give me vector k. The same way we can perform equivalent operations for k multiplied by I or j multiplied by k. It will always be pointing in the direction of the third vector.
Manorama Horizon. Learning made simple.